Okay. Yes.
I'm in conversation with Stuart Martin from ESRI South Africa, and I asked him a little while ago about remote sensing and the possible use of remote sensing in disaster management. And then there are a few interesting proposals and things that we can do in disaster management. So I just asked him for a conversation regarding this, and he will tell us more about remote sensing, satellite imagery, and so forth, and then the use in disaster management. Hello, Stuart.
Hi, good morning, Herman. How are you?
Yeah, fine, thank you. Yeah, you have listened to me, so it is now over to you.
Okay, fantastic. Thank you very much. Good morning or good afternoon. I'm going to be talking about the use of satellite imagery in support of disaster management. And we all know there's preparedness, there's mitigation, there's response, recovery, etc. And I'm going to touch on a couple of these areas and how satellite imagery is used and how we can use it to support operations, to understand the implications, etc. But I think the first thing to talk about is what is satellite imagery and what are some of the properties of satellite imagery that we need to be aware of. So the one thing is the spatial resolution, and that is exactly what can we see on the image. And we typically talk about low, medium, high, and very high satellite image resolution. And the pictures on the right are illustrating the top pictures, what we would call your traditional Landsat satellite imagery. It's a 30-meter resolution. The pictures just below that on the right is a spot satellite, which is at 2.5-meter resolution. And the image on the left is a very high resolution 30-centimeter picture of exactly the same area. This is the Lapalale Wilderness School up in the Waterberg in Limpopo province. And it's just indicating how far we've progressed in the quality and what we can see on a satellite imagery, but they each have their uses and they each have their benefits. So keep in mind that sometimes we do not need to have very high resolution satellite imagery for some of our requirements. And you'll see that a bit later in what I'm talking about. The next issue is that of what are we actually seeing? So is it a panchromatic picture? So it's a black and white or grayscale picture, or is it a multispectral picture, red, green, blue? And then a lot of the new satellites are giving us infrared information, so in shortwave infrared, near infrared. Some are going down into some very specific bands regarding vegetation, such as red edge and xanthophyll. And then we have water vapor bands and aerosol bands. Those we use to try and understand cloud cover and where there are clouds on an image. Now, a very good example of this is on the right is a picture of a school to the east of Pretoria. And in the top picture, you're seeing a natural color. So it's just a red, green, and blue image. And it's showing you the sports fields around the school. You'll note that the field or the hockey field in the middle is green. However, when we look at a near infrared image of the same area and we're visualizing this as a color infrared image, you'll note that it's not red. Red's typically what vegetation will look like, and we're seeing chlorophyll levels in vegetation, and suddenly the grass is not red anymore, it's highlighting as blue. This means that this is a astroturf, so we're able to pick up things that even if they painted green, the satellite through its multispectral capabilities are showing that it's not really vegetation. So this is something that becomes very valuable when we're looking for things and classifying satellite imagery. The next thing is temporal resolution. This is typically our revisit time. How often are we able to get access to a satellite image? We are at a point in time now that you can get a satellite image over most areas in the world every day. Now, yes, there's cost implications of that, but in the case of disaster, you need to know exactly what's going on very quickly. What's happened in the satellite space over the last couple of years are two significant issues. The one is satellites have become very agile, and what I mean by that is that they're able to point. So the satellite is not just always facing down in what we call nadir. It's able to move around and take photos at different angles, which means that even if the satellite's not crossing Durban last week after those floods, we are still able to take a photo of it at a slightly oblique angle, and you'll see some of that just now. The next issue is that we are getting more and more flocks of satellites. So we talk about a constellation of satellites and not just one satellite anymore. And this means is that you're getting multiple satellites orbiting the Earth, which are giving us more and more revisit time. And I'll show you a picture of what these things look like. The next issue is the difference between active and passive sensors. Now, a passive sensor is typically an optical sensor. It's looking at the solar radiation as it's reflected from the Earth, and that's where we get our near-infrared, our shortwave infrared, and our red, green, and blue values. An active sensor is something like synthetic aperture radar, where we have a sensor which is literally sending energy down to the Earth. It's bouncing off the Earth's surface and coming back to us, which means we are able to see through clouds. We're able to see at night. And we will use an example of that in Cyclone Idai, where in the middle of whilst the cyclone's ongoing and just after the cyclone, we find that there's a lot of cloud cover, which means it's very difficult to take satellite imagery in the traditional sense, and we use active sensors there. Just for a visualization, this is a satellite called Worldview. This is Worldview 3, and this is about a 2-ton satellite, fairly large. You'll note by the people standing next to it, it's a fairly large piece of metal, and that needs to get launched by a fairly large rocket to get it into space, to get it in its prerequisite orbit. And there's one satellite called Worldview 3, there's a satellite called Worldview 4, and these are used to collect imagery. The pictures on the right, that is not a model of the satellite, that is an actual CubeSat. The top picture is a picture of a satellite built by Kaput, the Cape Peninsula University of Technology, and launched through Space Commercial Services and the company called Pink Matter. That is the satellite. It takes satellite imagery. The bottom picture is of a Planet satellite. They launch these satellites, multiples at a time, up to 60, 70 of them, and they put them in orbit from the space station. So you're suddenly seeing, moving from the left to the right, there's a difference in the size of the satellite, and then logically that means you can't expect the same quality from the right-hand image that you can from the right-hand satellites that you can from the left-hand satellites. However, you can get daily revisit times, and these are the things that we get excited about. Then finally, when we started using them many years ago, it was typically about downloading a satellite imagery, and we spoke about rows and paths. The satellite is continually orbiting the Earth in a path, and we would then have a row on that path where we would get a satellite image from. We are now in a situation that we get access to mosaics of imagery. So it's not about one picture anymore, it's about a picture of the whole world. And this we get through the web. So we are streaming imagery to us, to desktops, to mobile. We can process that imagery through a cloud-based solution, and sometimes when required, we need to download that imagery. So think of satellites now not just about a physical one satellite picture, it's about having access to satellite imagery over a large area, and we are able to get very detailed content through the multispectral, and we're able to get data on a fairly regular basis, up to daily. So I'm going to jump to another area in the slideshow where I'm going to talk about some of the applications of this. So the one thing I'm going to speak about here is something like construction management. Now, we're using a Worldview satellite. This comes from a company called Digital Globe, 30 centimeter resolution. We can task it to revisit an area literally daily if we needed to. And this is about monitoring change. Now, this is the Medupi power station in the north of South Africa, in Limpopo, near Lephalale, and that's what it looked like in 2013. This is a more recent imagery in May 2017, and then finally that was an image from the 6th of April 2019, and you can see there's been a lot of progression in the building of the power station. To illustrate the type of quality that one can get from that, we are able to see that type of detail down at a 30 centimeter resolution. This is taken from space. Now, an example which we've all been very aware of from a disaster perspective was the fire at the Notre Dame Cathedral in Paris. So there's an image of the cathedral as it stood in February 2019. And I gave this presentation 2 weeks ago, and a day before the presentation, I was able to access that image 2 days after the fire of the cathedral. Now you'll note how the buildings are leaning. This is how the satellite has needed to point to take the photo, because it wasn't flying over directly. But there you can see the roof is missing, and that was one of the things that burnt. Now last week we had a fairly large rainfall event in Durban area, down to Manzantoti, eThekwini. And this is, you might have seen the pictures of the harbour with all the plastic floating in the harbour. So this is one of the small craft harbours in the bigger eThekwini harbour. This is a picture taken earlier in April. That was a picture taken in the middle of last week. And there you'll see a lot of debris and inside the water, and that's typically all your plastics which have been washed down the stormwater system. Another example, this is the eThekwini River on the 14th of April, and showing it's still fairly significant river, but it's contained within its banks. This is a satellite image taken after the event last week, and you'll note that a lot of that vegetation has been pushed flat. You can see some of the areas where cars were parked, they'd been moved away so they didn't get flooded. So you are able to understand the extent of that event. This is very much after the fact, but we're able to understand what happened, where was the flood, and what was the major extent of that flood. The next example I want to show is one of a recent event in Mozambique, where we had Cyclone Idai. And here I'm going to discuss the issue of bringing multiple sensors together. So we're going to fuse imagery together to assist in things like, how could we have prepared for it? How do we respond to it after the fact? And here we're using a multitude of sensors. The first two, Sentinel-1 and Sentinel-2, those are sensors which we get from the European Space Agency. The JAXA ALOS DSM is a Japanese space agency sensor which we use to create a digital surface model. So it's a height model of the whole area. And then worldview is something we saw a bit earlier in context of the Durban floods and the fire in Paris. And this is we use this in conjunction with machine learning and artificial intelligence, and a company called Ecopia Tech captured the structures. So they physically put a point on every structure across the whole area. So let's look at this. This is a satellite imaging in January around the area of Beira. You can see the river mouth at Beira in the right side of this image. And you're seeing a fairly flat area, very green, very lush, but you can note that there's certain areas there which seem to be a bit wetter than others. Just because they're darker green, it means the vegetation's a bit more lush. Whilst the cyclone was ongoing, and just after it hit and made landfall in Beira, you'll note we weren't able to get a very clear satellite image because there's a lot of cloud cover and there's still a lot of water in the atmosphere. But here we're picking up all that brown is water. So those are places that are inundated in water. There's floods going on in that area at that point in time. But now, how could we have quantified that? We've got cloud cover. We have a fairly significant event. Those two images were Sentinel-2 images, which are optical data sets. What I'm showing you now is a Sentinel-1 image, which is it's an active sensor, and it's synthetic aperture radar. So this is an image from the 13th of March. And once again, showing you roughly the same area, the river mouth coming out at Beira. And you are picking up that where those areas are slightly darker green, there's more moisture in those areas, and you're picking it up there. But let's look at a satellite image taken whilst Cyclone Idai was ongoing, and that's illustrating the flood inundation in that area. This is a significant extent of water. Now, the question here is now what is going on here? Is this a densely populated area? Are there a lot of people living there? What is the impact from a disaster recovery, disaster preparedness point of view of that area? So let's look at it in a bit more detail. What we've been doing at ESRI South Africa is creating a model, and Herman's very aware of this. We've used it before in a disaster preparedness project in the Northern Cape, is to look at digital surface models. So here we're using the JAXA, or the Japanese Space Agency, digital surface model. It's a 30-meter surface model, which is adequate for this. And we build what's called a flood potential model. So all the areas in white typically won't flood. The areas in a lighter green have a flooding to, say, a maximum of 1 meter, and the areas in a darker green have a potential for flooding higher than a meter. And once again, you're starting to see a pattern. Next to the river, on the opposite side of Beira, you're starting to see that it's darker there. So this is low-lying areas, a very dense drainage structure, etc. But if we put that in comparison to the satellite imagery illustrating the flood extent, you start seeing a lot of correlation, that our model seems to be doing the right, approximating flood inundation or water level rise in a very accurate way. So, but we can't see too much there, so we'll show that a bit later. This picture, every one of those black dots illustrates a structure. So it could be a freestanding structure, it could be a structure within a village, it could be a pump station, etc., a pump. But that's illustrating where people live, where there's land use activity associated with people. But a better example is to go in a bit closer. And this is an area along a drainage line, showing you where people live. Now, your immediate reaction might be looking at that as well. Look at the proximity to that river running through it, and that's the modeled river using the digital surface model. You'll very quickly think, wow, these people most likely had a very high incidence of rain, of flooding in this area. But let's see if that was true. So we could preempt that cyclone by detecting drainage lines and running our model. So then when you look at this model, you'll note where it's dark green, we say there's a higher depth of flood inundation. The lighter green is a potential to say up to a meter. And then the areas where you're still able to see the satellite image, you are realizing that that's a very low potential for flooding. And if you see the correlation between that and where the people live, there's a very strong correlation. The people have built their structures in most cases in higher lying areas along these drainage lines. Let's look at the satellite imagery of the same area, and the blue showing water versus the white showing a lack of water. You start seeing that that is true. There are houses in the floodline, there are houses that are inundated, but a lot of the areas were not impacted by the actual rise in water level. When we put all of this data together, so the digital surface model and the modeled flooding, the satellite imagery, and these structures captured from satellite imagery, we can start understanding the impacts and where would there be a lot of people who are in dire need of assistance versus areas which aren't. The challenge these people face is how do they get in and out, how do they get food, have their small-scale farms been damaged, have they lost livestock, etc., etc. So one is able to use this from both preparedness and mitigation point of view, but also post-event to understand the implication and extent of what was going on. So that's what I'm showing you now. Back to you, Herman. Is there anything else you'd like me to talk about?
Yes, it's very interesting, Stuart. Yeah, especially then the relationship between the actual data or the rainfall data or the streams and the flood area, and the model that you have created, so that we can apply that in other areas as well before a flood, for example, to do your disaster risk reduction planning and see where can we evacuate people to and during the event. So this help a lot for planning as well beforehand, because now you can simulate that with, like you said, through computer learning or artificial intelligence to apply that in other areas as well. Before a cyclone and before a flood, and that is important part of disaster management is the planning before an event. So this will be very helpful. Thank you, Stuart. What I think in the future, if I get any questions regarding this, because I want to put it now on blackboard for the students to see or then to distribute it to them, is if there's any questions, I will forward that the questions to you, so that you can also communicate with the students or other people that have questions regarding your presentation.
Perfect. Herman, just one more comment. One of the areas where we have been involved is using these models and using land cover models to illustrate where helicopters could land. We know and we saw on the news that helicopters were used extensively in support of the mitigation and to try and rescue people who had been left with serious challenges after the water rise. The problem is the helicopters need to land in areas, they need to refuel, they need to be maintained. So you need to find areas close to where the crisis is, where helicopter bases can be built. And one of these models are used in support of things like that, yes.
Very interesting. Thank you, Stuart. So like I said, I will direct the questions to you in the future. Thank you.
Okay.
Bye.